All right, we're going to take a look at 7.1, which is developing systems of linear equations. So we say systems because we're not just going to write one linear equation now, we are going to write two. A system is multiple. Okay, so for example, a school district has buses that carry 12 passengers and buses that carry 24 passengers. The total passenger capacity is 780, and we know that there are 20 more small buses than large buses. So to determine how many of each type of bus there are, we can write two equations to model this situation. First, we must identify the unknown quantity. So what are we looking for in this idea? So what we're looking for is how many people can fit on each bus. That's what could be found from this situation. Because we have 12 passengers on one bus and buses that carry 24 passengers to a total capacity of 780. So we have both small buses and large buses. So let's say let S represent the number of small buses. And let L represent the number of large buses. Okay, then we need to come up with the two linear equations that model this situation. So I've underlined my information in two different colors because we're going to write two different linear equations. Red, the school district has buses that carry 12 passengers and buses that carry 24. So there's two different sizes of buses, and in total, the school division has enough to carry 780 people. So this is describing the number of people, okay? Therefore, on a small bus, the number of small buses times 12 would give me the number of, S, would give me the number of people carried on all of the small buses, because each one carries 12. Again, if I did 24 times the number of large buses, we could get the total number of people carried on large buses. All together in this school division, that needs to add to 780. Then we can talk about the total number of buses. It says there are 20 more small buses than large buses. So we have more small buses than large buses. Therefore, if we have small buses, take away large buses, the difference between those two would be 20. So I've color-coded so you can see where I'm getting the information from for each of my equations, and I'll try and keep doing that for you guys. So these two equations form a system of linear equations in two variables. Two variables because we have S and L. We don't have three variables. A system of linear equations is often referred to as a linear system. A solution of a linear system is a pair of variables that satisfy both equations. So if we found L is equal to some number and S is equal to some number, and that was true for both equations, where the numbers worked out, we could say that this was our solution to the problem. All right, so we're working on today, we're creating the linear systems, and then later on we will be solving them. So create a linear system to model this situation. The stage at the Lyle Victor Albert Center in Bonnyville, Alberta is rectangular. Its perimeter is 158 feet. The width of the stage is 31 feet less than the length. So I'm just going to draw a quick diagram for us here. So we have this stage and it has a width and a length. So we need to define these two variables. So let W represent the width of the stage. Now, I'm going to say basically the same thing, but I'm going to say let L represent the length of the stage. These little like two dots or two lines mean that repeat what was said above. Okay, so let L represent the length of the stage is what that would read. I just We're going to write this out a bunch of times. Every time we write out a system of linear equations, we should be identifying our variables. Okay, so there's two equations we need to make from this data. The stage is rectangular and its perimeter is 158 feet. Well, with that number and my two variables, I should be able to get an equation. Remember, perimeter is where we would walk all the way around the stage. So I could say that it was L plus W plus L plus W, and that'll equal 158. And we can simplify this just to 2L plus 2W equals 158. So that's our one equation that we're going to use. The other one, the width of the stage is 31 feet less than the length. So what is longer is what we're going to write first. Remember, we want this to be a positive number. The length is longer than the width by 31 feet. So length take away width will equal 31. And I say that we need to put the large number first so that we can get a positive number here. If you switch these two, you will have the wrong answer in the end. Okay. So those are our two equations that we would use to model this situation. Sebi has determined that the stage is 55 feet long and 24 feet wide. Use the linear system from part A to verify that she is correct. So we just need to sub into both equations and hopefully they work out, aka each side is equal, or left side is equal to right side. We'll prove that. Okay, so 55 feet long, meaning that's the length, and 24 feet wide, meaning that's the width. So let's sub into our perimeter equation first. So 2 times 55 feet plus 2 times 24 feet is equal to 158, hopefully. 2 times 55 is 110. 2 times 24 is 48. And hopefully that's still equal to 158. So I'm just carrying through what I know. Adding these two numbers together, I get that 158 is on the left side, and we still have 158 on the right side. Because the left and the right are equal to one another, this is true. Now, something can be true for one equation, but not the other, so it's important that you check in both in this instance. So, length was 55 feet, take away width was 24 feet, and that should equal 31. So solving the left side, we get that 31, 55 take away 24 is 31, and our right side is still just 31. Because these are equal, this is true. The stage is 55 feet long and 24 feet wide because it works in both. It is a solution in both equations. Create a linear system to model this situation. A school raised $140 by collecting 2,000 cans and glass bottles for recycling. So a total of 2,000 cans and bottles. The school received 5 cents for a can and 10 cents for a bottle. So we need to decide what our variables are going to be. So we're looking for the number of cans and bottles. So let C represent the number of cans collected. Now I'm going to say let B represent the number of bottles collected. So information that we could use for each equation. They totaled $140 and we know that we get 5 cents for a can and 10 cents for a bottle. So the information is a little scattered. So we're looking for monetary values for our first equation. So we get 0.05 of a dollar for each can and 0.10 of a dollar for a bottle. And when we multiply the number of cans by the amount we get per can and the number of bottles by the amount we get per bottle, they raised $140. Then they collected 2,000 cans and bottles. That means that the number of cans plus the number of bottles equals 2,000. So the school collected 1,200 cans and 800 bottles. Use the linear systems to verify the numbers. So sub into both of your equations here. So 0.05 times the number of cans, which was 1,200, plus 0.10 times the number of bottles, which is 800, should hopefully equal 140. So working to solve here, I get 60 plus 80 equals 140. When I add the left side, I get 140, which still equals the right side. So that's good. We're going to do the same thing with the other equation. So 1,200 cans plus 800 bottles is equal to 2,000, hopefully. Well, when we add them up, we get that 2,000 is equal to 2,000. Because the left side equals the right side, this holds true. A bicycle has 2 wheels and a tricycle has 3 wheels. To create a situation about wheels that can be modeled by the linear system below. Explain the meaning of each variable and write a related problem. Well, we have 2 variables here, B and T. So I'm assuming that one is about bicycles and one is about tricycles. So let's say that let B equal the number or represent the number of bicycles, and let T represent the number of tricycles. All right. Now I knew that this was number of tricycles, not wheels or something like that, because 2 times bicycles plus 3 times tricycles equals 100. Well, something about a bike, well, it has 2 wheels and a tricycle has 3 wheels. So if I multiply 2 by the number of bicycles and 3 by the number of tricycles, I'm counting wheels. That must mean there's 100 wheels. So in this first equation here, 2b plus 3t equals 100. There are 2 times the number of bicycles and 3 times the number of tricycles. And this equals 100. All right. Well, that sounds good. And then in the other equation, we have b plus t equals 40. So the number of bicycles, oh my goodness, spelling bicycles, plus the number, and the number of tricycles is 40. That means the total number of bikes is 40. So I wrote a little scenario here. I said that Gavin's bike shop sells bicycles and tricycles. The total number of bikes in the shop is 40, and there are 100 wheels in the shop. And that describes both of these scenarios. There are 100 wheels in the shop and 40 bicycles. All right, so again, the total number of wheels in the shop is 100, and there are 40 bikes in the shop, and that can be represented by these 2 equations here.